Thank you very much, and thanks for the invitation. In fact, that's the second longest title in the conference. Okay, I will talk about Gröbner bases today in a special sense, and the application I have in mind is the Cauchy problem for systems of partial difference equations with constant coefficients. I will start with this Cauchy problem or initial valued problem for simple systems. Then I will explain the words which appear in the title. Then I return to the Cauchy problem, and then I will say something about computing those Gröbner bases. So the very simplest case is one ordinary difference equation in one unknown. There are coefficients AD up to A0 in the field. The right-hand side is a sequence V, which is known, and the W is another sequence which we want to compute. And there is a simple way to do this. We isolate the highest order term, and then we see that we can prescribe the first D values of W freely, and then we can compute the sequence recursively. This is, I think, something which you learn in school or at the latest at the first semester at university, but there is another nice method to do it. It's just a little bit more complicated. We write down the characteristic polynomial of this difference equation, and this polynomial acts on the space of sequences by shifts. So I mean that if we apply S to a sequence W, then we shift the sequence one position to the left and cut off the first entry. So this S is short for shift. And then we can write down the equation in a very simple way. F applied to W is equal to V. Okay, that's where the algebra comes in. And if we want to compute W at time t, we can do it with polynomial division, because W at t is nothing different than the sequence W shifted t steps to the left and then evaluated at 0. So it's S of t applied to W at 0. Now we do the polynomial division. We divide S of t by f and get the quotient q and the remainder r. We insert everything, and the operation agrees with the addition and multiplication in the polynomial ring, so we can split it up. Then here appears the term f applied to w. We use the equation because that's just v. And then we get the result is the quotient applied to the right-hand side, evaluated at 0, plus the remainder applied to the sequence itself, evaluated at 0. And if you write it down, that's just this expression. And the important part is that the remainder has degree at most d minus 1. So here only the first d values of w appear. Actually, I think that's a very nice method, and it gives an idea on how to generalize it to more general situations. If we have several equations in still for one-dimensional systems, if we have several equations in one unknown, then we substitute these systems by the system given by the greatest common divisor of these polynomials. And for several equations and several unknown, we have to use some kind of Smith form or Hermite form to solve the system. The important part is the relevant algebraic objects are in the first case the ideal generated by the polynomials, and in the second case it's the row module of R. Yeah, and the recipe to generalize results for polynomials in one variable to polynomials in several variables is Gröbner basis. So instead of univariate polynomials, here we have polynomials in several variables. Instead of the greatest common divisor, we use Gröbner basis algorithm. Instead of division with remainder, we use the normal form algorithm. And the solutions here in the one-dimensional case are just sequences of time. And here we have sequences which are indexed by a tuple of non-negative values. Okay, so let's look at some examples. The first one is the binomial coefficients. The difference equation is well known, and according to our recipe, we get the the solution, the definition space of the solution is the first quadrant. And okay, in the one-dimensional case, the initial value set is everything up to the degree of f, so it's the complement of the degree set of the ideal. The same holds in the n-dimensional case. So the result is the degree of this polynomial here is 1, 1. This term is dominant no matter which term order you choose. So the result is this. We can prescribe the binomial coefficients on the x and y axis, and in this area, in this gray area, we can compute it. Looks fine, but it's not what you usually do, because usually we want to prescribe the binomial coefficients for n over 0 and n over n and compute the values in this wedge. So the beautiful theory does not work. Another example is the discrete diffusion equation. The solution should be a function or a sequence of time and space, and I have no problem to ignore negative times, because for engineers the future is more important than the past. But space extends in all directions, so I want to have the solution in this half space, and this is not what the Gröbner basis theory provides. Also, the operator is not a polynomial, because we have here s2 to the minus 1, so it's mixed polynomial, Laurent polynomial. Okay, so we have to start over. The problem here is the choice of solution space is more or less a result. You have no fundamentally different choice here left, whereas choosing the solution space, or choosing the definition of the solutions, the definition space of the solution should be something which you do in advance. You should probably do it simultaneously with defining your equations, and choosing the method should come afterwards. And this is what went wrong here. So we have to define suitable domains of definitions for the solutions at first, and we have to do it in a rather general way such that the examples are included. And both the half space here and the wedge here have the structure of a finitely generated affine monoid. The definition is it is a set which contains 0 and it is closed under addition. And it should be finitely generated, and this means that there are finitely many generators written in the rows of matrix theta, such that every point in the monoid can be written as a linear combination of these rows where the coefficients are natural numbers. Let's take a look at some examples of the quadrant. So the generators are circled in red. We have the quadrant, the half space, and the full space. And we have also more complicated shapes where some holes may appear. So I think this looks general enough such that the problem should be included there. Once we have such a monoid, we can define the sequence space where the arguments of the sequence are points in the monoid, and also the monoid algebra, which consists of all those, let's say, polynomial expressions where the exponents lie in the monoid. There is also a scalar product defined as before by shifts. S to the mu applied to W at point nu is W at point nu plus mu. And this makes the sequence space a module over the monoid algebra. And in the case of the binomial coefficients, the wedge is given by the two generators 1, 0 and 1, 1. And the solution is defined over the wedge, and the operator is also an element in the monoid algebra once we multiply it with S1. That's a technicality here, but it doesn't change anything. Okay, so in order to solve the Cauchy problem for difficult problems, we would like to have a Gröbner basis theory for submodules over this monoid algebra, just like we have it over the polynomial ring. And in this talk, I will restrict myself to Gröbner basis for ideals, and this, in the terms of the difference equation, it means that we have only one unknown. So W is one sequence and not a vector of sequences. Okay, let's recall shortly the definition of Gröbner basis. Gröbner basis is always defined with respect to term order, which is a total order. 0 is the smallest element, and it agrees with the addition. And once we have this, we can define what the degree of a polynomial is. We can define the degree set of an ideal. But it's in general difficult to compute this degree set. That's where the Gröbner basis come in. A Gröbner basis is a generating system of the ideal, such that the degree set of the ideal can be written in this simple way. So the degree set can be read off the Gröbner basis. For each element in the Gröbner basis, we have to take its degree and add the positive quadrant to it, and then we take the union, and that's the degree set of the ideal. The first important theorem is the existence and uniqueness of the normal form. Every polynomial can be written as uniquely as a normal form plus something which lies in the ideal. And this also solves the ideal membership problem, because the polynomial is in the ideal exactly if the normal form is 0. Once we try to do this for monoid algebras, we run immediately into the first problem, because in general there are no term orders for these monoids. In the simplest case is the set of integers. So if we want to have a total order where 0 is the smallest element, then 0 is smaller than 1. And now it should agree with the addition, so we can subtract minus 1, and we can subtract 1 from this and get minus 1 is smaller than 0, and so 0 is not the smallest element. So term orders only exist if the monoid is pointed, and this means that 0 is an apex. So we have to weaken the conditions of a term order, and for this we need a so-called conic decomposition. We have a non-pointed monoid and decompose it into several pointed ones of the same dimension, and then a term order is a generalized term order should be a total order where 0 is minimal. This is what you really need, such that the Buchberger algorithm terminates. But the addition only has to be, it has only to agree with the addition in a limited sense. Such an inequality is preserved only if you add on both sides an element which is in the same of these pointed monoids as the larger one. So the important thing is here, this nu is nu and eta are both in the red shaded area, and this suffices. We can define the degree of an element of the monoid algebra. We can define what the degree set of an ideal is, and we can define what the Gröbner basis is. It is a generating system of the ideal from which you can read off the degree set in a very simple way. So it's a little bit more complicated than in the usual case, but it's still simple. For each polynomial in the Gröbner basis, we have to look which of the pointed monoids it is in, and then we add this pointed monoid to it. So the degree set is here also the shaded area, and the complement are the points drawn in red. There is also the same normal form theorem as in the usual case. And we can solve the Cauchy problem using this Gröbner basis. And the calculation is exactly the same as in the one-dimensional case, which I showed at the beginning. W at some point mu is equal to W shifted by this mu, evaluated at 0. We compute the normal form of S to the mu with respect to this ideal and the generalized term order, and get this unique way to write, quasi-unique way to write it. The normal form is unique. We insert this, use the equation here, R applied to W is equal to V, that's the equation we start with. And then we get a summand which, where the right-hand side appears, and another summand where the solution itself appears, but it's the solution only in the complement of the degree set, because the support of the normal form is in the complement of the degree set. And this means we can prescribe the values at the complement of the degree set freely. So that's the initial value region, and in all the rest we can compute it. And you can even say, yeah, there is even a unique solution once you prescribe the value in the initial value region. Let's take a look at the diffusion equation. We choose a generalized term order such that the S1, so that on the x-axis is dominant. And this means that this S1 here is the leading term. The degree is 1, 0. Okay, this lies now in both of the pointed monoids. So we have to add both of them to it. And this means the degree set of A is the gray shaded area, and the complement is the y-axis. We can prescribe it on the y-axis and compute it in the rest. That sounds plausible. And if we want to compute it at position 5, 2, we need these initial values here, which are crossed out, and these values of the inhomogeneity. This is, I think, very plausible. And this has been developed by Franz Bauer, Sandro Zampieri, and Andreas Unterkircher some time ago. They gave the definition of the Gröbner basis and also an algorithm for the computation. And I was actually very happy to find this, but then I realized that nobody uses it. And once I started trying to compute some solutions of the Cauchy problem with this, I realized why it was. Because this Buchberger algorithm works directly in the monoid algebra. This means that you have to completely re-implement the Buchberger algorithm. That's a lot of work. And this was only the first part of the problem. The second part is it was not known whether such generalized term orders exist for arbitrary finitely generated monoids. So I did not know if I could use the theory for my problems. So that's where my work started. I found a new algorithm, and the idea behind the algorithm is that a finitely generated monoid has a finite generating system. In other words, the monoid can be parameterized by a quadrant. And this means that the monoid algebra is parameterized by a polynomial ring. So the idea is to transport the problem to a problem in the polynomial ring, use the usual Gröbner basis methods, and then transport the result back. The catch is that here in the monoid algebra we have additional structure, the decomposition in these pointed monoids and the generalized term order, and we have to choose the generating system of the monoid and the term order on this polynomial ring in such a way that it is compatible with the structure here in the monoid algebra. And that was a little bit complicated, but I found a way which I will show now. We start with a monoid given by some generators. Then we consider the convex hull of these generators. This is a polytope. The polytope has facets, and some of the facets do not contain 0, and those are the interesting ones. Then we can take a look at the cones which are generated by the facets and get a picture which is just like the picture I wanted to have. So now we have decomposed the monoid into several pointed monoids if we take the points in the shaded area. So that's the conic decomposition. And the second step is how to find the term order. Each of the facets defines uniquely a linear map, which is constantly 1 on the facets and smaller than 1 in the polytope. So these are the maps FF here. And then we define a map F, where for each point in the monoid, we take the maximal value of these linear maps FF. This is the same as looking in which of the pointed monoids it is in and taking the respective map FF. And then we can order, when we have to compare two elements of the monoid, we compare them first by their values under F. And if they are equal, then we take an arbitrary group order. So for example, a lexicographic order. And it turned out that this works. So by this we have a generalized term order. And we can also compute this compatible data in the parameter space. And this is not a simple step, and we use explicitly the map F here. So I did not manage to, when I started with an arbitrary generalized term order, I did not manage to lift it to the parameter space. So I really had to choose a special generating system and use this map F explicitly again in defining, when I was defining the term order in the parameter space. Yes, but it worked, and now I can compute solutions of the Cauchy problem in an automated way. And yeah, what I've shown you today is how to construct generalized term orders, how to what Gröbner basis that there is a Gröbner basis for monoid algebras, how to compute this Gröbner basis, and how to solve the Cauchy problem using all these tools. The results are published in this paper in Journal of Symbolic Computation, and I hope that this paper is only the beginning, because there are several things which I can think of which are left to do. I would like to extend the theory such that it includes, for example, elimination theory, a way to compute radicals of ideals, or primary decomposition of modules. This should in the end be implemented in a nice package, which I hope that Victor will help me. And the last point is perhaps the most challenging point. I have shown you a way to produce one generalized term order, or several term orders, but these are not all. I'd like to classify all these generalized term orders just in an analogous way as there is for the polynomial ring, where you can write every term order as applying as a lexicographical order after you apply the matrix with real entries. So that's Robiano's theorem. All this is part of a larger project which I am applying for currently, and well, I hope that it works out. Thank you very much. No, actually not. I don't expect problems with elimination. So the question was if I expected problems with eliminations, and the answer is no. Once you are able to choose the term orders freely, I mean, once you have a method to construct these generalized term orders, then I expect that you can just choose the right one in the same as you do in the polynomial ring.